Hello and welcome back for another special VMK in the game development series. In this VMK, I'm going to show you how to modify the first-person shooter game engine to work as if it's a third-person game engine. This slight change can make the feel of your game so much more different. Instead of looking through the eyes of the character that you're controlling, instead you're looking from behind the character that you're controlling. There's a little bit of math involved to make this work because the camera that you're now controlling has to pivot about the center of the location where the player is getting drawn. It's no longer the center where the camera is located. This is a subtle detail, but it's very important to make the distinction here because if you don't make this distinction, the players will get very confused very easily inside of the game. So let's go into our game engine and see it working. We're just going to start a new game. Now, what I've done here is I've just taken a 3D model of a character and mapped it to be located in front of the camera. So you can see it being rendered there, and you can only see the back of him because anytime that I move the camera is always pointed at his back. As I'm rotating the camera, the player is also turning. Now, I haven't incorporated any animations into this, so as I'm walking, you notice his legs aren't moving and his arms aren't swaying or anything like that. In this third-person camera view, you can see that no matter where I move, the player always remains in front of me. Even when I press the jump key, you notice that the player jumps and the camera moves upward with him. So all of that is being programmed now to handle the third-person camera view. The distinction which I was talking about earlier is this. Notice when I walk the player up right to the very front of these barrels. If I turn left and right, notice that the camera is pivoting about where the player is being rendered on the screen. Notice we're spinning around where the player is. If you try to do this action under the first-person camera view, you'll notice that you're actually pivoting or spinning about the center point where the camera is located in 3D space, not at the point located somewhere in front of the camera. Here you notice that I'm actually rotating in front of the camera, so I can place the player beside the box, rotate around him, and he doesn't actually move. If we didn't do this correctly, you'd notice that as I'm spinning, the player would be sweeping across the ground and it wouldn't look very realistic at all. So that's the third-person camera view. We're going to go into our code and I'll show you how to implement this. I'll give you all the math tools to do the transformations between the camera space and the person space. So it's going to be very easy for you guys to implement. So let's go into our code and take a look at how we're currently handling our first-person shooter camera. We're going to go into our scene library, and in here we see that we created this class called player. And player was responsible for keeping track of when we move our player around in the 3D world, as well as when we jump and crouch and do other things like that. Player was inherited from a class called camera. And if we take a look in here, this is the class that has all the speeds associated with how quickly we can move, and it keeps track of which direction we're looking, where we're positioned, things like that. As well as we have this mouse look parameter here that lets us to invert our mouse in the vertical direction. Now what we're going to do is we're actually going to scrap this methodology of inheriting player from camera and separate these two classes altogether. We're going to have one class called camera class that's only going to be responsible for figuring out where is our camera in 3D space. We're then going to have a player class, which is going to be responsible for keeping track of our player within our game, but this player is not going to be directly linked up to the camera using inheritance. Instead, we're going to be passing the values of the position, orientation, things like that from the player class to the camera class as if it's just a regular function call. We're going to need to do this because you can imagine that inside of a game there would be more than one camera inside of the game. And you'll want to be able to switch which camera is currently outputting to the screen, and it doesn't necessarily have to be the one that's associated with the player. It could be maybe you want to be able to see through a monster's eyes, or maybe you want to be looking through a camera within the game that is like a security camera and it's moving around looking at things. So like if the player looks at a computer screen and it wants to see what that camera sees, well, then you would have to have this ability to look through this arbitrary camera. So that's why we're splitting these things up. Because we're splitting them up, we can also change the architecture of how the game OpenGL class here uses our cameras. So we're going to go ahead and do that in this VMK. The major thing that we're going to be changing in this VMK is how our view that we're rendering to the screen is being calculated. If we take a look inside of game OpenGL, inside a frame, anytime we're playing the game, we go and call update game. And inside here, you'll see we handle the keyboard, there's some console stuff here, we update the player's position, and then we call this function called render pre. In this VMK, we're actually going to be removing this render pre function call because we won't need it. Instead, we're going to copy a lot of this code here and implement it back in the update game function. But anyway, in here you see we set up our perspective matrix, we have model view matrix set up to be identity, and then here this is where we're initializing the direction of which the camera is pointing. It's based on the rotation angles that the player is currently looking in, as well as the position of the player. We can get that here, and then we update the gluTranslateF function call. So in essence, what we see on the screen is being calculated right here using these two gluRotateFs and gluTranslateF function calls. Instead of doing it this way, we're now going to use a OpenGL library function call called gluLookAt. And this function works a little bit differently than what we've been doing over here. We set up a framework so that we have three vectors. One vector represents our current position in our 3D scene. Another vector represents the position that we want to be looking at inside of the 3D scene. And the third vector represents which direction is up in the world. Using these three vectors, OpenGL is able to calculate the appropriate 3D matrix to then represent the 3D world on our screen. So this is what we're going to be using. Let's go into TrueSpace so I can give you a visual representation of how this framework works. Imagine that this cone here represents our camera that we're going to be using to look into our 3D scene. So the direction that the camera is pointing is basically the apex of this cone. So imagine that you are sort of standing here at this open end of the cone looking directly inward towards the point here. And the sphere is just a representative point of the center of your location. So it's in the direction that you're looking at. This is the framework that we're now going to follow when we're going to be using our new camera positioning technique. There's going to be a relationship between the position at which the LookAt point is located and the up direction. Now we're always going to say that up is in the 0, 1, 0 direction, meaning positive y is up, and we're not going to change that. You'll only ever want to change this if you're programming like a flight simulator game, in which case you can roll the aircraft in 3D space. In which case then you would have to roll your up direction accordingly. But for us, we're not going to change the up direction. It's always going to be pointing straight up. When we're going to be moving around in the 3D world, we're going to be moving both of these guys together. So in other words, if we're moving forward, then we're going to do something like this. We're going to take the point that represents our current position, which is going to be represented by this cone, and we're going to take the point that's represented by the LookAt position, and we're going to translate them in the same direction, same amplitude, everything exactly the same. So moving back, we're going to do that. Moving forward, we're going to do that. If we're strafing to the left, we're going to do this. If we're strafing to the right, we're going to do this. So both items are moving together. Now, if we're turning our heads, that's where this new technique is going to work a little bit differently. Remember, the sphere represents the direction we're looking at. So, if we want to look to the left, what we're going to do is we're going to say the position that we're looking at is going to move to the left, but we're not going to move our own position. So what we're going to get is something like this. I'm going to take my LookAt point and move it to the left. And notice automatically our look direction here will change to face our point that we're looking at. Again, if we decide to look towards the right, so I move our look position towards the right, then our look direction here will always point towards the direction we're looking at. So this is the way we're going to control whether we're looking left, whether we're looking right. Same kind of thing when we're looking up and down. This is a side view here. So if I take my sphere and move it up, you notice that our cone pitches upward to maintain the look at direction. Same thing when we're looking downward. So just by controlling the location of the sphere or the look at point, we can control the direction at which we're going to be looking at inside of the 3D world. This is in essence what we're going to be implementing. And the way we're going to do this is we're going to have these three vectors that we need to keep track of. So now let's go into our code and start implementing this. To start, we're going to go into the camera class here, and we're going to rewrite this class so that it's now going to use the gluLookAt function calls from OpenGL. So here's the new camera class. We are going to define a constructor and a destructor. We'll have a set function, which lets us set those three vectors I was talking about, the position of the eye, which is where we're located in 3D space, the position that we're looking at in 3D space, as well as the up vector that tells us which way is up. And by default, we're going to set this up to be 0, 1, 0. We'll also have a render function, and this is what we're going to call anytime we want to look through this specific camera. All the sort of coordinate transforms inside of OpenGL will happen whenever we call render. The member variables, there's just three of them, and these are the three vectors that we need to know so that we can position ourselves, we know where we're looking, and we know which direction is up. Now that we've implemented that, let's go into our camera.cpp and write the source code for these four functions. Inside of the constructor, we're going to initialize our three member variables. The position, we're going to place ourselves in the middle of the world, so at 0, 0, 0. The center location which we're looking at is just going to be 1 unit in front of us. Remember the coordinate system in OpenGL, left and right is x, up and down is y, in and out is z. So -1 in the z direction is actually 1 unit in towards the middle of the screen. Up again is set to be 0, 1, 0. The destructor doesn't need to do anything, so it's blank. Our set function, all it's going to do is it's going to take these three values that get passed into here and save them inside of our member variables. Then render, all it's going to do is it's going to set up the model view matrix, initialize it to be an identity, and then take those three vectors and pass them into gluLookAt. If we open up MSN for help on this gluLookUp function, you can see what we need to pass into here. And if you read through here, you can see we need to position the eye, we need to position the reference point where we're looking at, and we need the direction of the up vector. And here's a little bit more of a description of what's going on. So we're just taking those x, y, z components and passing them all into our function. And that's it. So now our camera class is pretty stripped down and easy to use. What we need to do next is go and update our player class. We no longer want to inherit from the camera, so we're going to remove this, and we're going to need to modify some of these functions in here as well. Our player class now looks like the following. We still have some player states and crouch states and the mouse look. We're leaving those as they are, and then in here we can see we now have class player, no inheritance. We're going to have a constructor, which we're going to pass in a value that represents how far away is our point that we're looking at with respect to where we're positioned. We have a destructor, a set speed that determines how quickly we're going to be moving throughout the world, set mouse Y, which lets us change the inversion of our mouse, set position, which changes the location of ourselves in the 3D world, and we need to also pass in the direction that we're facing whenever we call set position. So that we can update both the position that we're at as well as the vector that represents which direction we're pointing to or where the look at point is. We have the move function, which lets us update our actions. The update function, which will call anytime we're doing jumping or crouching. And then we also have getPosition and getLookUpCenter. We'll need these a little bit later on to get the member variables out of this function. Our member variables are listed down here under the private section. We have the mouse look state, we have the player state, the position, the looking center position. So this is where we are, this is where we're looking. We have the looking distance. This is the distance between these two vectors. We have max up and max down. That is going to tell us what is the maximum angle upward as well as maximum angle downward that we're allowed to pitch our heads. We have the linear speed, angular speed, and then we have our jump parameters and our crouch parameters that we use when we calculate when we're jumping and when we're crouching. Down here we had a few inline functions defined up above, so down below here I'm just defining the getPosition is going to return our position, the getLookCenter is going to return our look center position as well. So let's save that, and now let's go into our player.cpp and write in all the other functions that we added into here. At the top here we have our constructor, which accepts one parameter, the looking distance. Down in here we're going to initialize all of our member variables. We have our state, which we set up to be walk. We have our look distance, which is the parameter we're passing in. The next two parameters are the maximum up and maximum down distance that we can look. It's calculated by taking the look distance, which is the parameter we're passing in, times the tangent of 30 degrees. And 30 degrees we convert to radians using this notation here, and then we're taking the tangent of that. Now what exactly is this doing? Let's go into PaintShop Pro and take a look. We have the distance from our position to where we're looking. That's just shown here by distance. We want to know what is the maximum up as well as maximum down that we're allowed to look. Our LookAt point, which is the red one here, is only going to be sliding up and down whenever we're pitching our heads up and down. So we need to know what is the maximum it can slide up and what is the maximum it can slide down. Well, the angle is what defines how high we can look or how low, and everything's with respect to this horizontal. So if we have some angle here, I've just labeled it angle, the tangent of that angle is defined as up divided by this distance. We want to know what up is, so we can just take distance times tangent of that angle and we're going to get up. Down is the same sort of thing, but notice that I'm going to be using a positive angle here rather than the negative. So this distance here is going to be a number, a positive number, that represents how far down we can go from our horizontal. So that's what this here is doing. I'm going to talk about this math thing after we finish implementing all the player and camera class. Our position initially is going to be set to be 0, 0.5, and 0. Remember, 0.5 was the distance above the ground that our eye level is at. The look center is 0, 0.5, and then we want to move the looking distance away from our current position to define where we're looking at. Our linear speed is 5 units per second. Our angular speed is 3 radians per second. I like to have my mouse inverted, so I'm going to set it by default to be inverted. And then I define the jumping properties and crouching properties down here. Our destructor is empty. Our set mouse Y, this guy is responsible for changing our inversion from positive to negative if we want to invert our mouse. Setting position, we pass in a position as well as a direction that we're looking. The position overwrites our own position vector. However, the direction is needed so that we can get the direction, multiply it by the distance from our position to our looking center to get a vector, and then we add that vector to our position. This will give us the location of our looking center with respect to our position that we're located at. Movement. Well, we need to do a few extra things in here. At the top, we define this vector called v3 look direction, and it's a vector that represents the distance from our position to our looking center. If we go into PaintShop Pro here and take a look at this figure, we could see that, okay, here's our position, here's our look at position. Our vector is going to be this guy here that goes from our position to our look at point. Knowing that, this describes our looking direction. Whenever we're moving forward, we want to move both our position and our look center by the same amount. And we do that in the direction that we're looking. So we know which way we're looking because we just calculated up above. That's this vector here. We multiply that by our delta time and by our linear speed, and that's going to cause us to move our own position by this amount, and we're also going to move our looking center by that same amount. So both are going to move together. Moving back is the same sort of thing, but instead of adding, we're subtracting. And notice that we're not moving in the y direction. We're only moving in the xz plane. Moving left and right, we need to get a vector that's perpendicular to our look direction. And before we had a vector that was called, I think, side direction or something like that. And we know we're only going to be moving in the xz plane. So to get the perpendicular to the look direction, all we need to do is swap our z and our x components and add a minus sign to one of them. Without introducing an extra variable to hold one of these while we swap them, what I've done here is I've taken the x component, stored it in the y value because we know we're not going to be using the y for anything. Then I'm going to take the z component, add a negative to it, and save it inside of the x. Then the z ends up getting saved with the old x value here, so we're actually going to pass in the y here. And then we're going to reset the y to be 0. So all this code here does is it swaps our x and the z and adds a minus sign to the z component, or sorry, to the x component. Once we have this, this now represents our perpendicular side direction. This is the direction that we're going to be moving in whenever we're moving towards the left. So we take the position as well as the looking center and we offset it by the looking direction times the delta time times the linear speed. And we do the same thing for the right sliding, but this time we're adding them rather than subtracting them. When we're looking, we need to do a rotation. A rotation in 3D space uses a rotation matrix, which I think I talked about earlier. What we need to do is calculate the sine and the cos of the angle that we want to rotate about. So again, we're going to take the time, the angular speed, multiply them together to get the angle that we're rotated. We're calculating the sine as well as the cosine, and then using those two values we can apply the following transformation. F sine times our looking direction in the z plus f cos times looking direction in the x. And then this guy will give us our x component. Our z component will come from similar kind of thing, but here we have f cos and here we have f sine. Don't forget to offset by our position so that we are locating our center at the right spot. Notice that the rotation here is moving our looking center. We're not touching at all our looking position. So if we go into here, here's the rotation. We have our position, it's at some fixed point, and we have this angle that we want to rotate about. Well, we can do a rotation matrix upon this vector. Originally this point might have been somewhere over here, let's say, and what we're doing is we're rotating about this angle. So we're leaving this point where it is, we're taking this guy and we're figuring out how much does he need to move in the xz plane so that he's positioned over here after the rotation. That's what we're calculating over here, and we need to offset everything by our position because we're not doing this rotation about the center point 0, 0. Instead we're rotating about our position, which is located right here. Looking right, we do the same thing, but the formula is slightly different here. We don't have a minus sign here, and everything else is the same. To look up or down, we're only going to be calling looking up. You'll notice that inside of the code, we never call looking down because the call that we do to update our position when we're pitching our head up and down comes from the mouse, and the mouse will give us a positive or negative reading. So based on that, we can just use looking up and all the calculations is exactly the same. To look up, what we do is we take our center point and we're going to be sliding it up and down. Remember, I was talking about that here. We're taking our position of the point that we're looking at, and we're just going to slide it either up or down to figure out how high up or how low down we're going to be looking. So to do that, we're going to take our center point and we're going to offset it by the delta time plus the angular speed and the looking state. We then check to see if we've gone too high or too low. If our Y position here is greater than our own position plus the maximum value upward, then we're going to cap it at the current position plus the maximum up. Same thing on the way down. If our Y position is less than our current position minus the maximum downward, then we're going to cap it at the maximum. So we need to know where this guy is in the vertical direction. If we know that, then we can say, okay, this position plus the maximum or this position minus the minimum is the range that we're allowed to slide this point up and down in. Jumping, we perform the similar kind of calculations that we've always done. We have the time step that we do here, and if we're walking, then we're able to jump whenever we call the jump function. We calculate a bunch of things in here. Crouching, similar kind of thing. Exact same code, I do believe. Some of the variables here might have been changed to just use the new position vectors and direction, but that's basically it. The player update, we call this to make sure that we update everything while there's a jump or while there's a crouch. So again, we're just using the same kind of formulas we developed way near the beginning. So take a look through here. Oh, and the other thing I forgot to mention at the beginning of this video is I am going to be giving you the code to camera.h, camera.cpp, player.h, and player.cpp. So you won't have to write this out. You can just use this code. I'm just referencing here so that you can understand what's going on. So there's, what was it? There's crouching, there's getting up, and that's it. Last function here, we have set speed. This guy is only responsible for setting the linear speed and the angular speed from our function here. Because these guys are private members, we don't have access to them from the outside, so the only way we can update these guys is by calling the set speed function. Alright, let's save all of this, and let's do just a compile and make sure that everything is okay. Oh, right, there's one thing with the math that we never corrected. Inside camera.cpp, everything's fine here. Alright, so we should probably go in and now implement the new math function calls that I'm using over here. You notice that I have this thing math, 2 colons, degree to radians. What I decided to do is create a static function call, degree to radians, and I grouped it inside of a math class so that I know that this function is responsible for some sort of mathematical computation, and it's a general function, so I made it static, which means I don't need to define a math class to be used. Instead, I can just use it anywhere I like. Because it's static, I just need to dereference the class using the math and then 2 colons, and then I can just pass in the name of the function inside of that class so that I can use it wherever I want. Let's go into our math library. Inside here, under the source file, we have a generalmath.cpp and generalmath.h. Let's open this up. We see in here we have a bunch of variables, 0, E5, pi, pi divided by 180, 180 divided by pi, and so on. What I want to do here is clean this up a little bit so that they're not just variables floating around in space like this. Instead, I want to group them to be inside of a class called math. Here's how we can do that. We create a class called math. It's going to have a public constructor, and it's going to have 3 members. They're all static, and they're all inline. And I've done this specifically because most of the math functions, we are going to be calling them a lot of times, every time through the loop, so I want them to run as quickly as possible. We have a function called is0 that's going to return a boolean based on a value that we pass in here. We have a function to convert from degrees to radians, and another one to convert from radians to degrees. Both of these return floating point numbers.
Our public members, they're all static. We can use these outside of the math class because they are static. So we have pi divided by 2, 2 times pi divided by 180, 180 divided by pi, 1 divided by pi, and 0. Then down here we have our inline functions defined. So degrees to radians, we pass in the degrees. To convert to radians, we just take our degree value, multiply it by pi divided by 180. Our radian to degree function will take in a radian value, multiply it by 180, and divide it by pi. Our is0 test is going to return a boolean if our value is greater than minus 0 and it's less than positive 0. And 0 is a constant value that's defined inside of this class that you're going to see what it's defined to inside of the CPP file. So that's all that we have inside of the general math.h. And again, I'm going to be giving you this code inside of this VMK, so you won't have to rewrite this if you don't want to. Our general math.cpp needs to be rewritten. And here's what it looks like now. Our constant floating point numbers that are inside of the class need to be defined if they're static. So here we go. We have pi 3.141592654, pi divided by 2. We have 2 times pi, and so on and so forth. Our 0 value I've set up to be 1e to the minus 7. Originally, I think we had 1e to the minus 5, but you'll notice that somewhere near the 3D modeling section, if you load in models from other 3D packages, you get these little black squares. To get rid of those, we needed to change our 0 value to be slightly smaller. So we changed it from 1e to the minus 5 to be 1e to the minus 7. And then down here we also have our blank constructor. We need this or else the compiler will give us a warning saying that this CPP file is not being used for anything. Let's save all of this, and we can go back inside of the player CPP and try to recompile this. Oh, I guess we should go and recompile math.cpp first, though. Let's see if that works. We are still getting an error here. Oh, we've made references to something called 0e5 inside of our vector3 class. However, we've changed now to use this new math method, and to get access to 0, we now have to do this, which means anytime we have 0e5, we should just replace it with the following. I guess I should really be reading the code here to determine what's going on, because we can clean it up slightly here. We have a normalized function, and we want to know whether fmag is less than 0. I think this is fine. We may want to just change this from being less than 0 to be less than or equal to 0. The next guy here is a 0 function call. Instead of doing all of this, we can now just rewrite this code to look like this. We're going to take the math function call is 0, and we're going to pass it in the x value, the y value, and the z value of our vector. If all of these are 0, then this is going to return true, which is going to return true to our is0 function for this function call. Let's take a look at the next guy. Oh, same guy, same one. Down here we have is denominator less than 0. Again, we can just update this so that it's using less than or equal to math 0. And over here, what do we have? Vector3 does not define an operator to convert between these two different types. Let's just rebuild this, make sure that that error still pops up. Oh, I didn't mean to build, I meant to compile. Oh, we'll just wait for it to finish, because it's going to bring up a bunch of errors, because we are changing our player class as well as a camera class at the same time. We have all these other changes now to be making because we've changed our math library. Might as well go in here and make these changes while we're at it. Math 0. So this is inside of vector 2. You'll notice we have the similar kinds of things that we need to change. Just quickly make these changes here. Okay, player, well, let's save this, and let's go back to our math library and work at this one at a time, just so we don't start confusing ourselves. Okay, here's our vector3. Let's open up our vector3.cpp and compile him. He's fine. We can close off vector3. We know he's done. Let's do the same thing with vector2. Open up the vector2.cpp, compile him. He's fine, so we can close him off. Alright, that's good. Our general math, we can compile him. He's fine. We can close him off. And player.cpp, can we compile him? Not yet. He's still getting this binary plus sign error. Let's take a look at the way we've implemented our vector3 to see if we have the ability to take a vector3 and add it to a floating point number. Over here we have vector3, and notice we have an operator minus, operator minus, operator minus equals, times, and plus equals. We don't have an operator plus to do the math addition for us with a vector and something else. We need to go into our vector3 and add this functionality. So we'll just scroll down to the very bottom. Well, we could kind of group it in with these other ones. Let's add it in here. What we have here is vector3 is going to be returned to us. We're going to use the operator plus, and we're going to pass in another vector3. To add two vectors together, we're just taking each of the individual components, x, y, and z, and adding them together. The return value is this new vector3 that we construct by passing in each of these components into the constructor. We also have an operator plus, and this guy doesn't really do anything with our vector. He's just going to return ourselves, because if we have a plus sign in front of our vector, it really doesn't matter if there's a plus sign there or not. So let's save this and make sure we can recompile our vector3. He's okay. So now let's go back into player.cpp and try to compile him. He's now fine. So we just finished modifying our player class and our camera class to use this new technique of having these three vectors that represent where we are in 3D space and which direction we're looking in. Now we can go in and start implementing the modifications we need to make inside of the game OpenGL and the scene classes, so that we are now using this new framework for the player and the camera. To start off, let's go into the game OpenGL. Well, might as well close these other guys off since we won't be coming back to them. Camera and player, we can close those off as well. So here we are inside game OpenGL, and we're inside of the render pre. Let's take a look to see where we call render pre from, and we see that we are inside of update game. So inside here, we handle the keyboard, do some console stuff. We are updating the player, and then we have clear color render pre update. We're going to change this because we don't want to be updating the player from within our game OpenGL class anymore. We're going to do that directly from within our scene. So we're not going to allow this to happen. All of this is going to happen inside of the update. The render pre, this is the only place that we ever call it, so what we're going to do is eliminate this function and take all of the important things out of it and place it right into this update game function call. To do that, let's just go into the declaration of this guy, delete him, and then back over here, I wonder if I can still go in here. Yeah, I can go in here. Let's just take all of this code, cut it out from here, delete this function, and then we'll go back into the update here, and we're just going to paste in what was in that function. Make some more room in here to take a look into. Now, we're going to leave this. We still want to handle the keyboard. We still want to handle the console. We're not going to update the player here, so we're going to delete this part. Clear color, we still want to clear it to be white, so we're leaving this. And we're also going to need to clear the buffer, so we're going to leave that here as well. We're going to select the projection matrix because we want to render things in 3D. We're leaving that. Now, handling the camera controls, all of this is going to happen inside of the camera class, which means we can delete all this because we're not going to need it here. After we set up the projection matrix, we're going to call the scenes update, and then we're going to go, after updating everything in 3D, we're going to change to 2D, render the HUD, and do all the cleanup stuff. This is our new update game function call.
Now let's go and modify our scene. We're going to be calling the update, so this is where most of the changes are going to be made. Let's go into there. Inside here, we just have some checks to make sure we have a scene graph before we go and render it. We enable the lights and then do a bunch of other things. There might be some extra code up above here in your source code, and that's from previous videos we did whenever we had animations. Well, before we go and render anything from the scene graph, we need to make sure that our camera is set up as well as our player. So to do that, we need to update both of those guys. We're going to have a member variable called m_player, and this is just our player class. We're going to call the update function on it to update it every frame that we want to render something to the screen. We did this before inside of our game OpenGL up here. You remember I just finished deleting it a second ago. So we've moved it now inside of here. We are going to also add a new member variable for our camera called m_camera. And here, after we update our player, we're going to set the position of our camera based on the position of our player. So we're just going to get the position from our player, get the look at center from our player, pass those into our set function, and then our set function is going to update our camera appropriately. Once our camera is updated, we can go and call the render function on the camera, which is going to set up the 3D projection matrix for the direction, the angle, and all that other stuff to make sure that the camera is showing the correct stuff inside of the 3D world. All of that is done inside of that render function. Now let's go into our scene.cpp and add these other classes that we need in here now. Just so that things don't get lost, what I'm going to do is take this guy and move him to the very top because he's kind of the most important thing inside of our game. So here we have our camera and we also have our player. Because we're doing this now, we need to scroll up to the top here and we'll need to add a new new include to include both our camera and our player. Like so. If you still have your camera and player inside of game OpenGL, you can go and remove them since you don't need them anymore in here. Okay, so now when we highlight m_camera, he's okay. However, if we try to compile this, you'll get an error because our player class has a constructor that you need to pass in a variable. However, we haven't done that. So that's why we get this error message here, no appropriate default constructor available. And you notice that it's on the construction of our scene class. If you take a look at, where is it? Player. Let's just quickly go into there. Player. We have a constructor for our player, and the constructor you need to pass in this look distance. To do this, we can go into our scenes constructor, and right at the very end here, just add colon, m_player, and pass in the value you want to initialize your constructor to. So we're setting it to be 1 here. Let's just save this and try compiling our code again. Get angle x doesn't exist. Oh yes, because we've restructured the methodology of the camera and the player, we now no longer need a bunch of the functions that we had written in here, because we're no longer going to be updating our player from our game OpenGL class. Instead, we're going to be doing it directly from within our scene. So inside here, we can go and delete all these extra functions that we no longer need. Player update we're not going to need. Get angle x, get angle y, and get player position are now no longer needed because if we need that information, we can get it directly from within m_player. After changing that, we need to also go into our scene and delete the functions that are in here. Player angle, position, don't need that. Player action, we're leaving that guy there. Okay, let's save him and try recompiling. Something else, set I level. Anytime we started a new level, we call load level data. And in here, what we were doing before is we're setting up the I level for our player. To do the same sort of thing now, instead of calling set I level, we no longer have that function, we instead have set position.
And set position, we'll just go in here, we see we have a position vector that we specify, 0, 0.5, 0. 0.5 is the height of our eye, and direction, which by default is 0, 0, minus 1. So we don't have to change that because that's what we're end up going to be using anyway. So let's save that and try recompiling. Okay, where are we now? Inside of the HUD, we had the option to show the player's position. And when we do that, we had this function called that we get the position x, y, z, and to get those values, we called mPlayers get x, get y, get z. We can clean this code up by doing the following now. We're going to create a vector, v3 position. We're going to call mPlayers get position, so we're going to get the position, save it inside of this, save it inside of our own vector here, and then we're going to do the same thing here, position the text, call it x, y, z, and now we just get the x, the y, the z components from v3 position. The minus signs now disappear because the position in 3D space is the actual position that we're using. We no longer have to worry about this whole camera position and player position. Player position is player position, so that's the value that we're going to be using. Let's try recompiling this. What else we got? Oh, I think this should be a capital P, maybe? Yeah. Looks like a similar kind of thing down here. We're inside console render. We are rendering the player position. So now again, we're going to get the player position and pass in x, y, z down to the very last parameters in here. Try recompiling again. And let's build it now. See if we've made all the changes needed so that we're using this new camera player model. I think I saw some errors up there. Okay. We've changed our math implementation for pi, which means that anytime we are using pi, we should go in here and use the new methodology for using those values. So here, math, we have 2 times pi, so we can use this parameter here. Here we have pi divided by 180. Math, pi divided by 180. Might as well just copy this. Looks like a few of them are popping up here. Another math pi. Okay. Let's just rebuild. Oh, we missed a few. Here we have, oh, we missed this one here. Pi times 2. Here's some more. Math pi times 2. Try rebuilding. Looks good. Now let's give it a run and see if everything still works. We can move around, back and forward, left and right. If we're scrolling, seems to all be working. Jumping still works, crouching still works. So there we go. We've changed the ability to move around in a 3D world using this new gluLookAt method. And looking up, you can see we can point all the way up. Looking down, we have a limit as to how far we can look. So that seems to be in place. Looking up, we've got to get pretty close to see the limit here. There's the limit. We can't go any higher than that. Looking down, there's my limit. You can change those if you want to look higher or look lower just by changing those values within our, where was it, player, right in here. I currently set it to be 30 degrees up, 20 degrees down from horizontal. So that's how we define our maximum looking up and looking down. So there we go. Hopefully you were able to follow along in this VMK. The next one is going to show you how to introduce the ability to add a 3D model as your player in front of the camera, and how we're going to offset the position of our rotation point so that we're no longer rotating about where the camera is located, but rather where the player is located.